We had a bit of homework over the weekend. It was simply one question, not one simple question, but simply one question where we wanted to find the acceleration. That question's up on the board now. We had a 10 kilogram object. We were pulling it at an angle of 30 degrees with a force of 50 newtons, but there was a coefficient of kinetic friction of 0.10 newtons acting on that. Now this object moves to the right. Okay, it moves to the right, just like a wagon does. When you pull it up at an angle, the wagon doesn't go up at an angle. The wagon goes parallel to the surface and goes along that surface. Same thing with this 10 kilogram box. What do we got to do first? Well, the first thing that I see is this. And what do we think when we see this? We don't like funny angles. So let's get rid of that funny angle. Let's go off to the side here, and let's resolve that 50 newtons at 30 degrees into an x and a y component. So here's my hypotenuse, it's 50 newtons. Here's my x side at 30 degrees. Here's my y side over here. Let's say cosine 30 degrees is equal to adjacent over hypotenuse. X ends up being equal to, I think, 43.3, is that right? 43.3. Thank you. And we're going to say the y component is the opposite side, so it's sine 30 degrees is equal to y over 50, or y is equal to 25 newtons. All right, so there's my little aside. I've just gotten rid of my 50 newtons. I can redraw this if I want, and I do want, in this case, to redraw it, especially in this problem. I've got a force to the right. It's 43.3 newtons. I'm going to call that Fx. And I've got a force upwards. I'm going to call that Fy. It's 25 newtons. As far as the horizontal motion goes, I don't care about the y component because it's not moving up or down. As far as the horizontal motion goes, I care about the force that's pulling it horizontally, the x component. So I'm going to say the net force is equal to the sum of the forces. In the x direction, that's going to be Fx plus anything else. Yeah, there is something else on the x-axis, right? Jordan, what is it? Sorry? No? What other force should be on the x-axis here, Jacob? Kinetic friction. It's going to act backwards, right? Force of friction. Now, we don't know what the value of that friction is, so let's get it. Let's get the value of that force of friction. Let's say Ff is equal to mu times the normal force. Mu is 0.20, easy enough so far. The normal force is 10 times 9.81, right? Wrong. For the first time, we're encountering a problem where the object is moving horizontally, but it's not a problem in which the normal force balances gravity. Why doesn't it balance gravity here? Why doesn't the normal force equal gravity in this case as it did in all of those other cases where we were pulling the object horizontally? Yep. The normal force has to, well, it's not moving up at an angle. It's moving horizontally. So the normal force doesn't have to overcome gravity exactly. Let's draw gravity and the normal force here. Gravity acts down. Normal force acts up. Why is the normal force smaller than the force of gravity there? You can see clearly that I have it drawn as a smaller vector, so the normal force is smaller than gravity, whereas usually it's the same value in these problems. Why is it smaller here? Do you know why it's smaller there? Why is the normal force smaller than gravity? Yeah, it's being helped by your applied force, right? By the y component of your applied force. So something has to balance gravity. Right? If this box isn't moving up or down, then the upward force has to balance the downward force. But this time, you got two upward forces. not just the normal force, but rather the normal force and the y component of the applied force. So what we're going to do here to get the value of the normal force is say Fg, the downward force, is equal to Fn plus Fy, the y component of the applied force. So it's these two forces combined that's going to give me gravity this time. Whereas in most of the other problems, it's just the normal force that's going to give me gravity. So the gravity is 98.1 newtons. The normal force is, don't know. The y component of the applied force is 25 newtons. So what we're going to do now is solve for the normal force, which is not 98.1, as a lot of you probably wrote down, but rather it's 98.1 subtract 25. So it's going to give me, what is that, 73.1? The normal force is smaller than the force of gravity because the normal force is helped out by a 25 Newton upward force that the guy is pulling with. You pull up with 25 newtons on the 10 kilogram object, well, then the ground doesn't have to push up as hard because you're helping. So let's fill in here my 73.1 newtons instead of my 98.1 newtons. .20 times 73.1 is going to give me 14.62 newtons. So now I can plug in all the other stuff. The net force is equal to the sum of the forces, but it's also equal to m times a. 10 times the acceleration equals fx, which is 43.3 newtons, plus ff, which is 14.62, but negative. 43.3 minus 14.62 is 28.68 newtons. Then we'll divide that by 10, and I end up getting 2.86 or 2.9 meters per second squared. How many people got 2.9 meters per second squared? What? Nobody? How many people said the normal force is m times g, 98.1 newtons? Okay, not a big surprise there. Not a big surprise. Does it make sense why it's not? Right? In most of those problems that we did over the last couple of weeks, up until we hit the inclined plane, the hill problems, we said the normal force was equal to gravity, and we kind of just blindly did that. Well, now we can't, because now we're coming into situations where they're not balancing each other out. Now we got to think about if they're balanced out, why they're balanced out. As I'm standing on the ground here right now, gravity pulls down on me with a force of 700 newtons. Since I'm not going up or down, then something's got to balance that 700. There's only one force, the normal force, so the normal force has to be equal to gravity. But if somebody lifts me up with a force of 300, I got 700 pulling down on me, and somebody's lifting me up with a force of 300, then the ground doesn't have to push up on me with 700 anymore. It only has to push up with 400 because somebody else is supplying the 300. The total, the force of gravity, to completely balance that force of gravity. That's exactly what we've got here, except no one's pulling up directly on this box. They're pulling up at an angle of 30 degrees. But there is, within that 30 degrees, a y component. 25 newtons of that 50 Newton force is an upward force. So that upward force, combined with the normal force, those two forces are going to balance the force of gravity. Therefore, we get a normal force of 73.1. Good? You guys feel okay with that? Okay. Tomorrow we're going to have ourselves another little quiz on multi-force problems. I won't tell you exactly what it's going to look like, although it probably won't be a question like that, where you have to get the normal force like that. We might do a quiz question or a test question like that, but we'll probably do a one or two more quizzes before we see something like that. So tomorrow's quiz will be on either a pulley or an inclined plane or some sort of combination of pulley / inclined plane. But I'll tell you, it won't be like that challenge question that you had where you had the pulley and the inclined plane and the elevator and the guy throwing the ball and all that stuff. It won't be like that. Okay, so pulley and or inclined plane. All right. Shift gears a little bit. Talking about energy, not forces, starting today. Energy may not seem to have anything to do with forces, but if you think about what energy is, the amount of work that we do on something, it's very closely related to force. Let's think about the energy that this desk has as it moves. How did it move? I pushed it. So in order to get kinetic energy, we have to apply a force. Okay, force is not energy, energy is not force, but the two quantities, force and energy, are integrally related to each other. You can't really have one without the other. We're going to define energy as the ability to do work. Now, it's not necessarily doing work right now. Ryan's binder is sitting on his desk right now. It has energy. It's above the ground. It has the ability to fall to the ground, but it's not doing anything right now. His hand is. His hand is writing notes right now. But his binder isn't doing anything right now. But it has the ability to do something. It has the ability to fall to the floor if somebody gave it a tap off the desk. Now, his hand, as he's writing notes, is doing something right now. It is doing work. So there's really two kinds of energy, right? Energy is the ability to do work. There's two kinds of energy, though. The first kind of energy relates to the work that's being done right now. Okay, Ryan's hand has that kind of energy as it's moving along the paper. What kind of energy does his hand have as it's moving along the paper? Kinetic energy. Good. Kinetic energy is energy of motion. It's work that's being done right now. Whereas the other kind of energy is the energy that relates to his binder that's not doing anything right now, but has the potential to do something later on if we give it a tap off the end of the desk. What kind of energy does his binder have? Potential energy. So our two kinds of energy are potential and kinetic energy. The kinetic energy is the energy of motion. It's the hand with the pen. The potential energy is the stored energy. It's energy that's not doing something right now, but still has the ability to do something later on down the road, the ability to do work. In other words, really what it boils down to is it's either kinetic energy or it has the ability to become kinetic energy later on. Ryan's hand has kinetic energy because it's moving. Ryan's binder has the ability to get kinetic energy if it falls off the edge of the desk and moves toward the floor. There's lots of subcategories of potential energy. We'll talk about two of them, but there's lots of them. Anybody want to take a stab at one or two examples of potential energy? One or two, even if it's just not necessarily types of potential energy, but just examples of potential energy. Give me something that has potential energy. Something that's not doing anything right now, but has the ability to down the road. Okay? Okay, good, perfect. Okay, in 22 days, you guys are going to go to West Edmonton Mall on your field trip. You're going to be sitting at the top on a roller coaster cart that's about 1,200 kilograms, 50 meters in the air, almost not moving. And then 3 seconds later, you're going to be at ground level going 100 kilometers per hour. That roller coaster at the top of the hill has potential. It's not doing much right now when it's at the top of the hill. But 3 seconds later, it's moving at 100 kilometers per hour. It's got a lot of energy when it's at the bottom of the hill. It's 1,200 kilograms, and it's moving at 100 kilometers per hour. That's a lot of kinetic energy. The type of energy that it had to get that kinetic energy was gravitational potential energy. So one of the types of potential energy we have, one of the types of stored energy we have, is gravitational potential. Give an example of something else that has potential energy, something else that can do something, can ultimately be converted to kinetic energy, but isn't doing anything right now. As I pulled back this elastic hairband and I let it go, did it go flying towards the back of the room because of its height? If I don't pull it back, if I don't stretch it out, it's going to fall down, right? So it has gravitational potential energy as it falls down. But that's not what's driving it toward the back of the room. Lewis, what's driving it toward the back of the room? Call it elastic potential energy. Can't do this. Elastic potential energy, right, as I stretch it, the stretched elastic or a stretched spring kind of works the same way, right? It allows it to gain enough kinetic energy that it will fly towards the back of the room. So potential energy is converted to kinetic energy again, but this time it's not gravitational potential, it's elastic potential. I'm going to put with elastic potential, actually, spring potential, because springs can work in exactly the same way. Anybody with another type? We're overlooking something pretty big here. Something pretty obvious, actually. Static. I wouldn't say static potential so much, because in the end, if something's not moving and it has the ability to start moving, it's something else that gets it moving, right? What is that something else that get it moving? Is it gravity? Is it the stretched elastic? You're all at rest right now. What gets you moving? There's got to be energy stored in your body. Otherwise, you're not going to be able to move, right? So what is it that gets you moving? What kind of energy is it? Your car sitting outside. You get in your car, you turn on your car, and you start driving. The car's moving now. Where did the energy come from? There was stored energy in the car, but what kind of stored energy is it? Fuel, yeah? So what's stored in fuel? What's stored in gasoline fuel, or what's stored in your fuel inside your body? Chemical potential energy, right? You ate your peanut butter sandwich this morning. You drank your juice this morning. There's chemical potential energy that's stored in that gives you the ability to function. Chemical potential energy is what we use for the vast majority of our energy generation. Right? When we heat our houses, which we have to do right now because it's cold outside, we burn natural gas. It's chemical potential energy stored in the natural gas. We drive to the store or to school, we burn gasoline. It's chemical potential energy that's stored in the gasoline. When we turn on the light in our house, oh, wait a second, that's electrical, isn't it? But where does that come from? Well, the vast majority of power generated in Alberta is generated by burning coal. The energy stored in the coal was chemical potential energy. So this is a pretty big one. Chemical potential energy is a pretty big one. In Ontario, they have hydroelectric dams to generate power, which is gravitational potential energy because the water is stored at a height and then goes down through this penstock in a turbine and generates power. They also burn coal, like we do. But they also in Ontario have some other kind of power plant that we don't have in Alberta. Geothermal is a good one, but geothermal is used more for heating houses as opposed to generating electricity, although it could be used for generating electricity because anytime you have hot water, right, you got the ability to do something with that, right? They have, I think, a couple of these in Ontario. They've got one in New Brunswick. They got them all over the United States. No. Nuclear. Good. I was going to give you the final hint, which was they used to have one in Chernobyl, and they used to have one in Fukushima, Japan, until they had this little meltdown issue with both of those. The kind that we're going to focus on this unit, gravitational, inelastic, or spring potential. But be aware that there are these other kinds as well. In Physics 30, we'll take a look at electrical energy. We'll also take a short look at nuclear energy. And in chemistry, obviously, you'll take a look at chemical potential energy. So take the sciences. You will learn about these. You're just not going to learn about all of them right now. We're going to focus on kinetic energy, which is the energy of motion, and gravitational potential energy and elastic potential energy. We'll write down a quick little note about this, actually. This is gravitational potential energy. It's energy stored due to an object's height. And elastic or spring potential energy is due to a stretched or compressed, right? It's squished. If you squish a spring, it works the same way as stretching a spring, due to a stretched or compressed elastic or spring. Now we have equations to describe all three of these. Two of them you'll have learned before in Science 10. Kinetic energy, which is the energy of motion, we would represent by EK, and it's equal to, do you remember this? EK is, I'm going to give you a little hint here, see if more people can figure this out. 1/2, you know this one now? Oh, you're so close. So close. Brian said 1/2 times the mass times velocity squared. That's where he's wrong. 1/2 times mass times, nope, Brian was closer. But it's still not perfect. 1/2 times mass times speed squared. Kinetic energy is a scalar. In fact, all energy is a scalar. And if the energy is a scalar, then we're going to use scalars to get it. Mass is a scalar. Mass in kilograms is a scalar. And speed in meters per second is also a scalar. You guys remember the units for kinetic energy? Yeah, good. Capital J, joules. Gravitational potential energy. EP is equal to, remember this one? This one's easier than kinetic energy. No squared involved in this one. Al, you remember that equation, don't you? Okay. Yeah, good. MGH. EP is equal to MGH. M is mass. G is, what's G going to be? Gravity, 9.81 meters per second squared. We'll make it a positive value, though, because we're talking about energy, which is a scalar. Make that a positive value. H is the height, and that's going to be in meters. Okay. Elastic potential energy is, of course, gravitational potential energy is, of course, going to be measured in joules. And our last one, elastic or spring potential energy. You've never seen this one before. We're going to say EP is equal to 1/2 kx squared. We're not going to go into detail describing that one right now. Okay, we'll do a little bit of kinetic energy here for a few minutes. We'll do a little bit of gravitational potential energy for a few minutes, and then we'll do elastic potential. We'll explain the equation a little bit better when we get to that.